So let us see question number 6. Give example of two functions f and g such that GOF is injective but g is not injective. Injective means 1 1, right? We have to check for 1 1. So function is given from natural numbers to integers. Okay. So they have taken the hint, given in the hint also. So we will try to use this hint. So first function is y is equal to x. Y is equal to x. Okay. So y is equal to, that is fx is equal to x, right? Is equal to x. So if we see with the help of a mapping diagram, we can see to it. We are having first set, we'll be having another set, and we'll be having another set. This is capital X, this is capital Y, and this is capital P. This is a mapping that is defined as F. This is the mapping that is defined as G. And what is F for G? It is this one, that is G of fx. Correct. It is defined from x to p. So x is a set of natural numbers. So 1, 2, 3, 4, 5, 6, and so on. This is plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, and so on. This is again 0, plus 1, minus, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, and so on, set of integers. Now, so fx is equal to x, that means f of 1 is equal to 1, f of 2 is equal to 2, f of 3 is equal to 3, right? So it is a mapping that is 1 1, we can see over here. So this we have to prove. Yes, we have to prove 1 1. So first f is definitely 1 to 1, that we can see from here. Now let us see g. G is not injective, so we will be taking another function, that is modulus of x. So modulus, we always know that it gives a value greater than or equal to 0. So modulus of 1 is equal to 1, and modulus of minus 1 is also equal to 1. So that means for different x, I'll be having the same y. So it is many 1, it is not 1 1. So g is defined like this. That means minus 1 will be mapped to 1, and this 1 will also be mapped to 1. Similarly, minus 2 will be mapped to plus 2, and plus 2 will also be mapped to plus 2. So this function is many 1. It is not 1 1. So it is not injective. Function f is injective, g is not injective. Let us see about g of fx. So g of fx means g of f1, g of f2, g of f3, and so on. So g of f1, what is f1? It is equal to 1. So that means g of 1. We need to find out g of 2. We need to find out g of 3. So what is g of 1? G of 1 is 1. G of 2 is 2. G of 3 is 3. So we can see this GOF function is 1, 1. 1 is having unique and distinct image as 1. 2 is having the image as 2. 3 is having the image as 3, and so on. So this function is definitely 1 1. Correct. Next. Question number 7. Give example of two functions f and g such that GOF is onto but f is not onto. So f is not onto means its range is not equal to codomain, or its range is a proper subset of codomain. Okay. So the two functions are given over here. Let us see it with the help of mapping diagram. So we are having a set x, we are having another set y, we are having another set, let us say it is p. So this is x, this is y, this is p, elements of X are 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay, we'll be defining a mapping F, we'll be defining a mapping G. So let us see F function first. Fx is equal to x plus 1. So if x is 1, y is 2. If x is 2, y is 3. If it is 3, y is 4, and so on. Right? So we can see over here that every element other than 1 is having its domain defined. So domain and range is given except for this one, that is the part of codomain. So we can say in this case 1 is an element of capital Y, but 1 is not an element of range. Therefore this function f is not onto. So function f is not onto, it is into. Correct? Now let us see regarding g. So g is defined like this. If g is acting on x, if x is equal to 1, g is equal to 1. So we'll make the mapping like this. Gx is equal to x minus 1 if x is greater than 1. So if it is 2, g of x is 2, that means it will be mapped to 1, right? Then if it is 3, it will be mapped to 2. If 4, map to 3, 5 map to 4. Okay, that means its codomain is fully exhausted, right? And when codomain is fully exhausted, so for G what we can say? For G we can say, since range is equal to, since range, let us say range is small y, is equal to this set P codomain, therefore G is onto. So we have seen that function f is not onto, but we have seen that G is onto. Correct? Now let us see Goff. So for Goff we can see the value of G of f1, G of f2, G of f3, G of f4, and so on. Right? So G of f1, that means G of 1. And what is G of 1? It is equal to 1. G of f2, so that means G of 3, G of 3 is 2. So it is equal to 2. G of f3, sorry, it is f2. So G of f2 is equal to T, correct. G of f3, so you are passing 3 inside, it is giving 4, and 4 is mapped to 3. G of f4, 4. So we are having every element that is being mapped in the case of Goff. So we can say this Goff is also equal to onto, because the set P is fully exhausted. We are having 1, we are having 2, we are having 3, and we are having 4. So Goff is also onto. So we have proved that Goff is onto, but F is not onto, that we have seen over here. Correct? Next question.